Dr. Clark earned his PhD in planetary science at MIT in 1980. Roger's expertise is in identifying and mapping minerals and other compounds on the Earth, other planets, and their satellites using imaging spectroscopy. He develops laboratory, telescopic, and spacecraft spectrometers and imaging spectrometers. He has published over 300 scientific papers, including papers on every planet in the solar system. His research includes discoveries of the compositions of planetary and satellite surfaces and mapping the locations of minerals on the Earth and planets. In 2009, he discovered widespread water on the surface of the moon. He also publishes on environmental issues on the Earth, such as ecosystems in Yellowstone, led by the USGS environmental assessment of the World Trade Center disaster, and developed a new method for measuring the amount of oil on the Earth's oceans and leading to the first quantitative assessment of the amount of oil on the Earth's ocean surface in the 2010 Deepwater Horizon Gulf of Mexico oil spill. Dr. Clark was a senior scientist with the USGS until October 2014. There were less than 50 of these elite ST scientists in the USGS, now retired. Before the USGS, he was an associate research professor at the University of Hawaii. Dr. Clark is now a senior scientist with the Planetary Science Institute. Please welcome Dr. Roger Clark.
Now, you left off some things.
I did.
You're a long-time ex-member of the Denver Astronomical Society and a telescope builder and an author of a book on astronomy. So, Roger's been with us for a long time. A lot of
I dropped out of the U.S. Out of the club for about a year, and I need to dropped out for a year and then rejoined because my email got screwed up and I wasn't getting notices. And so now it says I joined in 2019 or something, but I really joined in 84. Okay. So this is, I came up with this idea for the talk. Can you hear me okay? Okay. But then when I started putting it together, it was too big of a topic. So I'm going to give you a little piece of several mega projects. And to start out with, so I'm a team member on, or I was a team member on the Cassini mission, and I'm a team member on the Europa Clipper mission. So I get to retire if there's no extended mission when I'm 83. Let's see, how do we advance here? Oh.
If we could get it into full screen view for the people online, that'd be great.
Do you want to stop?
Okay. One of the issues with spacecraft, as opposed to, when you're looking at Saturn through your telescope or photographing it, you get the whole thing. When you're in a spacecraft, it gets up close, and this image is actually of Saturn and the rings. And here we can go through. Saturn is all covering the whole image. Little Mimas is up there. The A ring is down here. It's light passing through the rings is dark on the Saturn. And then these are the shadows of the rings, and that's the B ring shadow. And the C ring shadow. C ring is more transparent, and then the F ring down there. So sometimes we need really special software to even tell what the heck we're doing. So, like I said, this is it's going to be a talk from a waterfall, a very big waterfall. So we're just going to get a little bit of drink. I'm going to tell you more what my role and some of the things that I've been involved with, just a few of them, because it's been quite a ride, because Cassini was 2004 to 2017. And we were studying the rings, the moons, Saturn itself. We had calibration issues. It's quite intensive to run one of these missions. And I've been on like 3 missions simultaneously. That's why I stopped coming to meetings. They don't get out much to do astrophotography. So when I do go, I now have like 5 cameras and 5 trackers, and I set them all up because I only get out once every few months. So first, a little bit about imaging spectroscopy. So how many here do astrophotography? Just a few, well, you know what it is. And you've seen the emission nebula images with narrowband filters. Well, imaging spectrometers are like narrowband imagers, except where Hubble and the guys who do narrowband imaging with their telescopes, amateur astronomers, they do one filter in front of a CCD or CMOS sensor. But with an imaging spectrometer, we put the whole spectrum on the sensor and image all wavelengths simultaneously. And it can be hundreds of wavelengths that we image simultaneously. Now, you can't do that. Really is a 3-dimensional data set. X, Y, spatial, and wavelength is the spectral dimension. So 3 dimensions, you've got to put that on a 2D sensor. So instead of an image at once, you do a line at a time and scan the line. So with spacecraft motion. This is an instrument that was on an aircraft, and this is an image of Nevada. Oh, can people online see the cursor if I do this right? But I'll mess up hitting the. I'm not good with touchpads. So our eyes are very simple imaging spectrometers. We image, obviously, and we see color. That's the spectrum. So we can tell just from our everyday experience. Here's a nice picture of a mountain scene. This is the San Juan Mountains in Colorado. You can see the vegetation. We know it's vegetation by the color. We can see the mountains. We can see the snow. We can see the blue sky. We know the composition of each of these things. So just from our everyday experience and our simple color that our eyes do, we do imaging spectroscopy. But down here, the spectrum, and a lot of the imaging spectrometers cover the entire reflected solar range. So UV out to 2,500 nanometers, that's 2.5 microns. So the visible spectrum kind of, if I can get there's a rainbow down here, and above it is the spectrum from 0.4 to 0.7 microns. That's the visible range. So this spectrum here peaks in the green, 0.5, 0.53 microns. That's the green vegetation. So having a spectrum that's more precise than just our 3-color eye imager, we can tell composition. And then as we go out further, you see all the squiggly lines. I'm going to show a few squiggly lines, but you don't have, hopefully your eyes won't glaze over. I'll show a lot of images.
Unfortunately, what they can see online with your cursor, we cannot see on your screen here. So if you also point with your fingers.
Yeah. Okay. So I'll try and do both when it's important. The rainbow here, and this is the visible range. So 0.4 to about 0.7 microns is the range of the eye, and green is just beyond 0.5. So the peak in the spectrum is the green color we see in the vegetation. But further out into the infrared, and this is beyond CCD and CMOS sensors, we have these other ups and downs, and these are water. And if you can tell between the two spectra, the ones up here are ice, and these down here are liquid water and vegetation. You see the positions are shifted between ice, which is at like 2 microns, versus water, which is short of 2 microns. So we can even tell the state of matter as well as what it actually is. And the spectra here are of water. Water is an orientationally disordered crystal, so the absorption bands are not sharp, but that's the exception. Everything else is nice, sharp absorption bands. And I'll show some of those. We have an instrument called EMIT, emitted infrared. I forget what EMIT stands for. It was, but it's on the International Space Station. It's the new state-of-the-art imaging spectrometer. We just got it up last year, and it produces images like this. So on let's see, your right, is a visible image, and then these minerals are coded by the colors. And we do hundreds of minerals, and these are just a few of them. And this is a scene in Argentina. And then another set of wavelengths with this, narrowband imager is snow and whether the snow is melting or not. So the magenta color here is where the snow is frozen. And then we can see where it's cyan and blue, that's melting snow. So we're watching melting glaciers and melting snowpacks, lots of work for climate change. And we can do the same thing with an imaging spectrometer at the Saturn system, the Jupiter system. There were imaging spectrometers flying all over the solar system. We had one around Mars on Mars Reconnaissance Orbiter. It was just turned off earlier this year. It had been in operation for quite a while. The system that went to Pluto, that had an imaging spectrometer. Basically, any mission that goes up now pretty much has an imaging spectrometer. So on Cassini, I was a member of the visual and infrared mapping spectrometer, and it covered the UV 0.35 microns to 5.2 microns. For those with nanometers, that's 350 to 5,200 nanometers. The resolution was not very good, 1.7 arc minutes per pixel, but the advantages were millions of times closer, so we can see really fine detail. When we flew by some of the satellites, we could get resolution down to a couple hundred meters. The disadvantage of VIMS was designed in the 1980s and early 90s. We only had 64 by 64 pixels, but 352 wavelengths simultaneously. So we had to do a lot of mosaics. Basically, every imaging sequence was a mosaic. And this up here, this is the moon for those online, in the upper right is the moon Phoebe, and then the colored images are VIMS images as we zoomed in on a flyby. And then I think this image was like 60 or 70 frame mosaic. This is a NASA APOD. So by selecting different wavelengths, we can see different processes. The red here is looking deep into the atmosphere and seeing the thermal heat in the Saturn, deep in the Saturn atmosphere. Where it's dark are clouds, cooler clouds at higher levels. The green is where methane reflects light, so the sun is shining this way. This is the night side. And then we chose a wavelength at 1 micron, that's 1,060 nanometers for where ice reflects a lot to show the rings. And it shows the 3 different components nicely. So you can choose 3 of 352 wavelengths, or you can do analysis of the absorption bands and then make specific maps of composition. So the first thing is Saturn's rings. Everybody knows it's made of ice. It's dominantly ice. But the question really with the rings, from our long way away perspective, and even the closest Cassini ever got, we couldn't resolve individual ring particles. And the radar instrument was able to infer some of the ring particles, and they're several meter in size to car size to house size. And the question is, let's see on the next slide. Do the rings look like this? Is it the sun is over on the left edge here, and then out to 14 degrees. So big particles, and are there a bunch of little particles? That's what's logically you might think is there. I'm going to back up a minute. So we have all of these absorption bands here are water bands. So the 1.5 and 2 micron water bands. The main OH stretch in the water molecule is at 3 microns. That causes all the structure out here. If there was other compounds, the advantage, let me back up. In astrophotography, you do emission line photography. You're looking at emission from individual atoms. But in reflected light, we're looking at chemical bonds. So we don't get the individual atoms except through the chemical bonds. So we see all these water absorptions. We know it's H2O. If there were other things there, we would see them. And commonly on the other satellites at 4¼ microns, we see CO2, but we don't see any CO2 in the rings. The rings, while they're snow, ice, they're not white, they're yellow. So there's something absorbing in the UV, in the visible and into the UV. And to this day, nobody has proven what that absorber is. So one of the things to show, besides composition, we can do the rings, which one of these do the rings look like? Are there little particles going around, or are they like disks? Well, fortunately with Cassini, we're orbiting the Saturn system, so we get all kinds of views that you can't get from Earth. So we can look at, as we go in and around the planet, and phase angle, everybody know what phase angle is? It's the angle between the sun to the observer, the sun to the object to the observer. So when the phase angle is low, it's like opposition. And so the spacecraft was near opposition. We actually did get right at opposition and get the backscattered sunlight, like we see on the Earth from satellites, the glinting out the ocean, you could see that glinting out Saturn's rings. And then high phase angle, when we get to 180 degrees, it's in transmission, and we did that. So here's the VIMS had a solar occultation mode, so we could actually put the sun in the field of view and use that to get a transmission profile of the rings. And then at every single point, we have a full UV to infrared spectrum, and there's no absorptions. There's no isotopic. So that tells us that, whoops, went too fast. No. Computers. Okay. So these fine particles, or seeing a rim of flight around the particles, we should see an absorption bands if that's the case, but we're not seeing that. So what that says is the particles are big enough that any rim light is so negligibly small that we don't see any absorption bands for any of the rings, and that they have to be pretty opaque, large snowballs. Now, the other interesting side effect, let me go back, is when we look at it in forward light, not transmitted light, where it looks like a snowball like this, and we see the absorptions, we get the characteristic grain size of the snow in that giant snowball, and it's in the 20 to 30 micron range. We're probing in near infrared light. So one would expect with them bumping into each other, the particles would be flying out and there'd be this dust, but probably electrostatic forces, it just goes right back to the ring particles. Okay, so water is basically everywhere. If you haven't heard that there's a lot of water in the solar system, there's actually not that much water on the Earth. This little marble here is the amount of water in the Earth's oceans, and the very smaller amount added to that is the fresh water on the land surface. Most of the water is in the oceans, and there's more water in all the satellites in the outer solar system than there is on the Earth. There's now Europa. I'm going to talk about the Europa mission. There's not quite as much water as we have on Earth, but it's darn close. And I think it's actually more. There are different estimates because we don't know how deep the ocean is yet. So there's different models. It's approximately the size of the water in the Earth's oceans, maybe a little more, maybe a little less, depending on the model. And the Europa mission will help solve that. But Titan has, even though we can't really see the water, there's suspected to be a big ocean underneath that is more water than the Earth's oceans. And then most of the satellites are dominantly water. So here's some of the things that we found. I'm not going to bore you with detailed spectra that shows all of this, but yeah, the rings are mainly water. But in the satellites, we see water and small amounts of CO2. And then I am going to discuss Iapetus and Phoebe, where we do see iron, and this is controversial. We have trace detections of ammonia, and then, of course, Titan has all kinds of stuff in it. And the main things that VIMS sees is benzene, methane, ethane. The methane and ethane are liquid, so liquid oceans or lakes. So Titan in the visible, of course, is just an orange disk, smoggy, but VIMS, so in the visible, it's orange, but the CCDs go out to 1,000 nanometers and out further. So the Cassini imaging system, which was a CCD, could see at the longer wavelengths, could see the surface hazily. But VIMS, and this is an early one. Toward the end of the mission, we produced a better one, but I misplaced it somewhere. But anyway, you can see there's all kinds of structure and this is a false color infrared view. This isn't any real color because you can't get real color from orbit because it looks like that. And of course, the Huygens probe did land there, and everything that is seen in the Huygens probe is organic compounds. There are white-looking rocks in the way they showed their images, but there's no proof, and they suspected those were water. So you might see reports that they're ice blocks, but nobody knows for sure. And VIMS, in all its detections of the surface, never found a single spectrum with a hint of water, regardless of what you might read in the literature. So there was controversy for a while, and some of these controversies just have a life of their own and never go away. So here's a summary of some things that have been found in the atmosphere and on the surface. So Titan is a pretty interesting, probably the most interesting moon in the solar system that we should visit in the future. So how many have observed Phoebe and Iapetus on a telescope? You probably imaged it, so they're not that faint. Iapetus is a two-faced moon. On one side, it's very dark, and on the other side, it's bright. It's like magnitude 12 on the dark side is showing. And what's happening is Phoebe is outside of Iapetus and orbiting the opposite direction, and there's dust coming off of Phoebe, and it's orbiting in the opposite direction, and it spirals in and impacts one side of Iapetus. So this is Phoebe dust coating Iapetus. But the question is, what is that dust made of? And so what the prevailing theory before Cassini was that it's called tholins. And tholins is just organic gunk. And Carl Sagan and his lab championed this idea. And unfortunately, of course, Carl didn't make it through Cassini. And I was actually working with him right before he died. We were working on tholins. But the tholin model, turns out once we got VIM spectra, didn't match up. So what is it? So if we look at the spectra, and here's the gory details, but the best interpretation that we have between lab data and models that model these spectra, which I'm not going to get into that detail, but we have the ice absorptions, but in the dark material, it's dark and reddish brown. We have CO2. We have a water absorption, but it's not ice. It's shifted. So it's water that's bound to whatever the dark particles are. And there's only one thing that matches this slope, and that's metallic iron. And this is the same slope as on the moon. And this same absorber in this shape is also in the dark material on Callisto. So there's a commonality with this dark material throughout the solar system. And basically, it's not that exciting. So people still like tholins because it's organics. This dark metallic absorber is when you have a silicate, like a meteor or meteor dust or whatever, or any planetary surface that's exposed to space with cosmic rays and the solar radiation, it weathers and it destroys the silicate molecules there, but iron is left behind and it creates nanophase iron. And that nanophase iron creates this slope here. So that's the best explanation we have. But, so Iapetus is a reddish brown, Phoebe is grayer or even a bluish color. So this is the region of visible light. So the color of Phoebe is pretty much unchanged over the short wavelength region of visible light. So it's grayish. But Iapetus, you can see from that picture, is reddish due to the decreasing slope toward the UV. But so why is that? If it's Phoebe dust from here to there, why isn't it the same color? Well, it turns out once we started modeling these spectra that it's a matter of abundance. So on Phoebe, there's a lot of mixtures with ice. So all this cratering has churned up things. So the Phoebe dust is mixed with ice. So even though it's dark, it's a multiple scattering problem. You know, you get a little charcoal on a white shirt, it's going to be a black spot. So that's Phoebe's dark, but we don't see that because that mixture, it kind of neutralizes the red color. But on Iapetus, so much Phoebe dust has come in and covered up, and you don't see craters here because it's so deep in the dust that we're seeing the true nature of the Phoebe dust color. So it's a mixture problem. Now, there's a couple of other things that I'm going to get to here shortly. So while there's no or little ice in this spectrum, most of this shape here is bound water, and it turns out that water is common in almost everything. If we took a spectrum of anything here in the room, we'd see water in it. Even things that are hard, we'd see water. But so these big absorptions here are adsorbed water or trapped water in whatever structure the silicate mineral is. And these are also mostly bound water. So, but this is common in all minerals. So how unique is this to one mineral? Well, most of the time it's not unique, but in this one case, in fact, it's the only case I know of where this is unique. We only have water adsorbed on hematite, iron rust, which normally doesn't have water in it, but the water in it is at a unique position and shape, and that's the only match we have. And that's consistent with the rest of the story of meteoritic dust that has been space weather. Okay, now isotopes. So yeah, I was going to mention isotopes. So H2O, D is deuterium. That's hydrogen with nitrogen. Hydrogen is a proton, deuterium is a proton with a neutron added to it. And so we have deuterium detections also. So isotopes, almost everything has isotopes with it. Sometimes they're radioactive, but the lighter elements, hydrogen, carbon, oxygen, there's oxygen isotopes. We're breathing them in all the time. They're not radioactive. So, but different processes, because they're different weights. So a deuterium atom is double the mass of a hydrogen atom. Then, while the chemistry is the same, if it's in an atmosphere, the deuterium atoms will tend to be lower in the atmosphere, the hydrogen higher in the atmosphere. And if the hydrogen being stripped off, you'll get fractionation and you'll enhance the deuterium. So knowing what the isotopic ratios are can tell us about the history of in the solar system. Now, the origin of water in the solar system, and remember, you guys who are doing very commonly hydrogen and oxygen emission nebula images. Gee, that's the components of water. Water is probably very common in interstellar clouds, and in molecular clouds, the D to H ratio is very, very high. That 0.01 is huge. Let's see, in the interstellar medium, that's 1.6 times 10 to the minus 6, so part per million, but the Earth is a part per 10,000, and molecular clouds a part in 100. So in the formation of the solar system, the models say that from the inner to the outer solar system, the deuterium should be increasing. In the past, before 2019, it was the only way to measure deuterium is through the narrow absorptions in an atmosphere. So things like icy satellites of Saturn, it's so cold, there's no water vapor evaporating, so you couldn't measure the deuterium, the D to H ratio. And so we developed a method with Cassini to do that, and that was published in 2019. And remember, big water bands. So with parts per 10,000 deuterium, and because deuterium is higher in mass, and these are all, the wavelengths of these absorptions are due to the masses. So you double the mass, the absorption shifts outward. And this little divot here is the OD stretch. And there's two problems with trying to see that out here. Look at the reflectance here at 4.25 microns or 4.1 microns where the OD stretch is. We're at down less than 2% reflectance. That's darker than anything black in this room. So it's very dark. Plus the solar flux is dropping, it peaks in the visible and out in the infrared it's dropping. So we have very little light on a very, very dark surface. And trying to do that takes a lot of averaging. So we averaged a lot. I mean, you can see here we averaged 21,882 pixels for just the B ring alone. Then this is that same absorption down there blown up so we can see it. And we can see the scale there for the amount of D to H ratio. So, well, what does that mean? So remember the Earth was 0.00016. Oh, that's almost the same. It's not higher. So Saturn's rings have a D to H ratio that is the same as Earth, essentially. Within the error bars, it's the same as the Earth. So here's a summary of the green ones are what we found in the Saturn system with Cassini bends, and then other published numbers. And notice we only have one very poor number for Callisto, and that because this is with the Galileo instrument, which was much noisier than things we have today. So we will hopefully get D to H ratios for not just Callisto, but Europa, and even map the D to H ratio across Europa's surface, and also animate and put this in place. But the models are going up, but the observations are mostly, except for a few very Oort cloud comets, are just a little bit above the Earth line. So why is that? Why do we have a huge variation in meteorites? We have a fair amount of range in minerals on the Earth, but minerals on the Earth have gone through a lot of processes. So we would expect changes, but the bulk Earth, and BSMO is the Vienna standard mean ocean water. That's the accepted international standard. It's only a few percent different than the estimated bulk Earth. And the Saturn satellites within the error bars are either very right on or very close to the Earth line. This is totally unexpected. So this means, I mean, there are several scenarios here that you can come up with, and people are still working on this, and the people whose models are now destroyed are trying to trying to say this isn't relevant, of course. This has something to do with how the water was delivered to the Earth. Was it delivered from comets throughout the solar system? Was there a lot of mixing through the solar system where water was delivered close in as well as far out, and this mixing as the solar system formed? So that's all being worked out now, and putting more nails in the coffin of the water story will be with the Europa mission. And I'm not sure, has anybody here worked with JWST spectrum? I've reviewed a couple of papers so far, and JWST could get the GDH ratios in the Jupiter system, as well as the moons of Uranus and Neptune and a whole bunch of comets. But the spectra that I've seen so far have a strange gap right at 4 microns. So I don't know if it's a different mode of the spectrometer or what, but I just haven't had time to contact colleagues who are working on this to see what the story is. Could JWST do it? Well, we also did CO2, carbon 12, carbon 13 ratios, and here's the 4.25 micron absorption. Now, the absorptions occur in different places because it's bound H2O, bound CO2, and CO2 is not stable. If it was an ice, it would evaporate. So this is trapped CO2, and depending on which mineral it's trapped in, it shifts around a little bit. And then the 13 CO2 line is over here. So Iapetus, well, let's go to the lab. The terrestrial is carbon 12 to carbon 13 is around 90. In the lab, this lab spectrum, I measured it at 98 plus or minus 10. Iapetus is also about the same, basically terrestrial, but Phoebe is an outlier. Phoebe is such an outlier. It's an outlier in the D/H ratio, and it's an outlier in the carbon 12, carbon 13 ratio. And I mean, it doesn't even match anything we know of. Even the galactic center is the lowest we have. That doesn't even match there. So Phoebe's not from around here. It's not from the Saturn system. And maybe it's not from the solar system. I don't know. Okay. On to Europa Clipper. I don't know what I'm doing on time. Keep going. This is great. Okay. So Europa has long been, it's pretty well established. I don't know of anybody who disputes that Europa has an ocean, because Europa is being tidally flexed as it orbits Jupiter, so it's under constant heating through this flexing. And down deep, the water, the ice has to be turned to liquid because it's too hot. And we know that there's all kinds of structure at the surface of Europa. It's a very young surface. There's very few craters. So we see stuff that's been brought up from cracks and stuff. The only dispute that I know of, and maybe some of my colleagues here will tell me, oh, Roger, you're full of it. We know that exactly. But the only dispute that I really know of is how thick is the ice shell? And then second, from the bottom of the ice shell to the rocky core, how deep is that? And there are various models that give various answers. And, with the Europa mission, we should be able to answer that. Now, with let's go to the next slide. There's this ice shell has there's lots of different models for explaining all the really, really strange structures that are on Europa's surfaces. All of these are cracked. If you have a chance to go out on after a really strong cold spell high in the mountains and go onto a lake that is safe to walk on, where the ice is thick enough, you'll see many of these same kind of cracks, but on a small scale. But these are kilometers. I should with the scale bars on here. But these are many kilometers long, and the width is probably several kilometers. So these are huge cracks, and they're just all over the place on Europa. And there's different colors, so different materials being brought up. This crack here is a ridge where it's like a long geyser that has thrown up material from deep down. So this is ocean material from the deep ocean, and with the Europa clipper, we'll get in close and determine what the composition of these things are. And hopefully that'll tell us, composition of the ocean, some of the composition, some of the controversies that are involved. One of the big issues with Europa and the Jupiter system is the radiation environment is extreme. And so we don't go in and orbit Europa because it's difficult to do, it takes a lot of energy, but the radiation environment is so extreme, the spacecraft wouldn't last very long. So we're orbiting Jupiter and coming in periodically with close flybys to Europa, doing a correct data gather, get out of the radiation belt, send the data back to the Earth, and then go back and do it again and again. Let's see. So, one of the big issues with, all this strange structure and stuff being brought up from the ocean, if it's liquid water, it's warm enough for life. There's energy sources. We know there's energy sources because of the surface activity. There's been, I didn't show that, I didn't mention that, but there are plumes that have been seen, and the Europa Clipper mission will look for those plumes and hopefully even fly through them and sample them. But, once we get in there and start getting the chemistry, is that, doesn't have all the ingredients we need for life. And, life finds a way. So if there's an ocean, there might really be life. Now, to really know, you're going to have to go down. And so there are studies being done on how to drill down through the ice and put a probe down there. Depends on how thick that is. So the Europa Clipper mission should answer that. Then the design of if it's even feasible with our technology to get into the ocean. So here's some of the instruments that are on, all of the instruments that are on the Europa Clipper mission. So there's the UV spectrometer. It's an imaging spectrometer. The imaging system, this is equivalent to the imaging system on Cassini, but little newer technology. It's I believe they're CCDs, but I'm not positive. They could be CMOS, but I'm pretty sure they're CCDs. And then using filters, just like it was done on Cassini. MISE is the imaging spectrometer, and I'm on that team. And it doesn't go quite the range of VIMS. VIMS went from the UV 350 nanometers on out. MISE goes 600 nanometers out to 5200 nanometers. The eThemis is a thermal infrared imager. I think it only has 2 or 3 channels, so it's not an imaging spectrometer. Reason is a nice penetrating radar. So it's a radar similar to the one on Cassini. I think it may have a little bit different wavelengths to try and get deeper into the ice. Then in situ instruments, there's a mass spectrometer, a dust analyzer, magnetometer, a plasma detection system, and of course, if you're talking a spacecraft, you get gravity and through the radio science. So the gravity can through multiple flybys, can tell the internal structure of the moon. The launch is October 10th, 2024. So it's most of the instruments, fortunately, just in the last week or so, maybe 2 weeks, the MISE instrument team that I'm on, we delivered to the spacecraft. So our instrument is now sitting on the spacecraft and it's undergoing testing and everything's going well. It's very, very difficult to develop these instruments because, think of Sony developing a new camera. They have to go through all kinds of testing because people are going to drop their camera and they want it to survive and stuff like that. Well, launch is much worse than dropping a camera on the floor. It's vibrating, and so you got to go through vibration tests. Nothing should break. You have to do electrical tests, and all of these parts have to be spacecraft qualified and radiation hardened, and we're going into a very tough radiation environment, so it's even extra hard to design these instruments. There have been multiple Europa missions proposed over the last 30 years, and several of them have bit the dust, never got to the point of doing much beyond the initial studies because it was too difficult for the technology. And it's still difficult, so we're pushing limits all the time to get this mission to go and survive the Jupiter environment. So going to orbit April 11th, 2030. I think some of these dates may shift a few days depending on when exactly we launch and stuff, but it's pretty locked in to be close to that time. So that'll be exciting. Now, the MISE instrument, as opposed to VIMS, actually I have that here. The MISE instrument, this just shows a mother spectra of organics. If we can find organics, we see lots of absorption lines. We can do all kinds of chemistry with the details of the organics. But there are problems. There are unknowns that we don't yet know. And one of the big problems, planetary science isn't probably what you read about in the press. So there's this salts versus acid controversy. Has anybody heard of this? So back in Galileo days, early 2000s, some publications came out with the Galileo NIMS instrument, which is the precursor to the VIMS and the precursor to the MISE instrument. And this red spectrum up here is the Europa darkish material. And the early publications said it's salts. But they were only analyzing this part of the spectrum. And the problem with only measuring this part of the spectrum, or analyzing that part of the spectrum, is salts have water bands, acids have water bands, minerals have water bands, and they all occur at about the same location. And trying to get from this region a unique answer of what these other things are in the presence of ice was difficult. And then another group came out and said, no, it's not salts, it's acids. Now, acids obviously are not good for life. And to increase that, it's not shown in this spectrum, but another component that is found is hydrogen peroxide. Hydrogen peroxide plus acid is a common mixture that is used to destroy organic compounds in a chemistry lab. So we know there's hydrogen peroxide there. If there's acid there, the surface, of course, it's a radiation environment. It's not conducive to life anyway. But if the ocean was acid, then you can forget life, at least life as we know it. So this acid versus salt controversy has gone on for 20 years. And you look at these spectra and it's kind of obvious. These salts have this hump and all kinds of structure. We don't see that in this one Europa spectrum. To me, the controversy has been solved long ago. But the salt people, hang on, because salts are cool. We have a salty ocean that's more conducive to life. So they don't want it to go away. So we'll see when we get there. And maybe the surface of Europa is created acid due to the radiation environment, and the ocean is still salty, and maybe in some of these plumes that have come up from cracks in the surface, we'll actually see the salts and we'll resolve them. And the spectra from MISE will be more like these lab data. They won't be the noisy things up here. And this was an early acid mix spectrum I did before I built a new environment chamber system. Got to make some new stuff. Problem is lack of funding. And that's where I'm going to go next. So the planetary science, it's really going downhill. And not just that, all of American science is really suffering heavily. I don't know what it is in the physics world, but you look at this, these are numbers that have been from my own work and colleagues' work, what we've been able to get in funding, Galileo mission, and these are all normalized to 2018. And you see the downward trend. So at Galileo, there was this mantra, oh, well, this is not any longer Apollo. With Cassini, everybody was saying, oh, it's not any longer Galileo. We're in the lean and mean. Now, Europa, we don't have any funding until we get into orbit. We have no funding for lab work. We have no funding to develop software. How can you do a multi-billion-dollar mission and go 15 years with no added new technology? It boggles my mind. And this is the plot that was put in the congressional record a couple of years ago. This was a proposed, and the new proposal is lower. So it's down about here. I got to make a new plot and put it in, say, 2024 numbers.
So not just whole dollars, so it's just $100,000, or are we missing some zeros for the funding amount? Like for Europa, is it really just $100,000?
We get a few dollars to attend online telecons and attend one meeting.
Right, but the vertical scale looks way too small.
Yeah. Is the scale just true dollars? Like when you say 100,000,
is it thousands of dollars?
It's $100,000 per year. Remember, for an institute, you typically have 40 to 50% overhead. So at the investigation level, if you had 100K coming in from NASA, you'd have 50 to 60K to pay to buy your computers, pay for software, do travel, pay for a programmer. It quickly goes down to everybody's working for peanuts. And this is the state we're in. And the problem is because of this state, the researchers have been told to go to RNA. RNA is research and analysis funding. And the RNA is now so oversubscribed that the probability, if everybody put in a perfect proposal, less than 20% would be funded. So the probability to get funding is approximately 1 in 5. So you have to write 5 proposals to get one funded. And they won't fund, I forget the exact number, I think it's on this page. They will only fund not more than half a person a year per proposal. So you'd have to write 20 proposals to statistically get full-time funding for 1 year for yourself, let alone have for any students, programmers, anything else. I mean, it's really getting dismal. And so planetary science and what I learned from my colleagues, I'd be interested to hear what the physics community is like. It's really down to a part-time effort. So you're lucky if you're at a university or you're a university professor where you only need to, say, get 3 months of your salary, then you can survive in this system. But other places, I'm at a research institute that it's a nonprofit. We have to raise our own salary, and it's extremely difficult. Now, for me, I'm doing okay because I'm on a couple of missions. It's not very much money. I work 60, 70, 80 hours a week, and I get paid for 20 hours a week. But I love it. But that's what NASA is now trying for. And because I'm a retired government employee, I have a pension, so I can survive. I couldn't survive if I was not retired with a pension. I mean, I would have to go find something else. And many of my colleagues have given up and gone on to other things. So, I just wanted to present this. So get the word out whenever you can. and put it on social media. We need to get this word out. NASA's, there's no simple solution. The budget keeps ratcheting down, but maybe NASA, in my view, NASA's doing too much. They like beam counters. Oh, we got 46 missions. Well, we're only paying $10 per mission, but we're doing 46 of them. And that's going to lead to failures. Fortunately, and there were quite a few failures in the early 90s into early 2000s, where faster, better, cheaper was impacting stuff. Well, the engineers learned, hey, if you don't do this and do all of this checking and give us the budget, then your mission's going to fail or high probability of failing. And so NASA backs off and gives them the money and cuts the science because there's no money left. So we're constantly in this game. So anyway, I want to end on a happy note. There's plenty of water in the solar system. It's everywhere. We now know it's on the moon. Mars underneath, down, it's all frozen, but there may be as much water on Mars as there is on the Earth down in the soil. And then when we go out in the solar system, there's ice all over the place, and comets periodically deliver some into the inner solar system. So, in the long term, if we move out into the solar system, finding water should not be a big deal. Oh, and here's an interesting thing. You've all seen The Martian? The movie The Martian? Yeah, great movie. It showed some of the complexity. Not everything was right, but enough it was really good. And but we had an imaging spectrometer around Mars, and every single spectrum returned by it was because of compact reconnaissance imaging spectrometer for Mars. Every single spectrum showed water in the soil. And we have areas where there are higher amounts of water exposed near the surface. So all the Martian guy needed to do was pull up the images from the PRISM instrument and go to the closest location where he could have found lots of water. Anyway, and from that, he could have generated oxygen and so on. Okay, questions?
So when we were kids, we were taught that the rings of Saturn came from a moon that somehow gravitationally was ripped apart.
Yes.
What do we think now?
That's still the case.
Okay.
Yes.
If we wanted to advocate for more funding for science through NASA, would there be an organization that you would recommend over any others for supporting for advocacy?
It's probably go to the senators.
Okay.
That, while organizations can help advocacy, ultimately we have to convince our senators that it's worth it. To me, if you're going to spend $1 billion or several $1 billion to do something, don't shortchange the American public with little science. A mission like that deserves to be well funded to do the science. So back to, because we don't have the lab data, so we know imaging spectrometers work. We'll see things, like organics or salts or acids, but we don't know how to interpret what it means. We'll know that it's there, but until we do the lab work for what's the radiation processing doing? Is it creating this signal, or is this something that came up from the ocean and is stable and it's reflective of the ocean, as opposed to radiation damage that happens in the first 5 hours when it gets on the surface? Until those experiments are done, we don't know the meaning. And that's where the science needs that background in order to do its right thing.
Thanks.
I've read I'm a fellow MIT alum, so I'm excited to read another one.
I got my hearing aids, so I'm going to go.
It's okay. I was going to say I'm also an MIT alum, so it's nice to see another alum here. But the question I had for you is, I read recently that the core of the Earth actually has a lot of embedded water in the rock now as well. So is that part of your calculation when you show how much water is on the Earth? So not just the oceans and rivers, but also the core.
So the question was, recently a study came out and said there's a lot of water deep inside the Earth bound in the minerals. And no, that is not included in this. So, some of the hype in the press releases or the online stuff said oceans of water deep inside the Earth. Well, it's not really oceans, it's water bound to the minerals. And I don't remember the numbers, but it was some significant estimate. But, I don't know how we'd ever get it out because it's so deep. So it's more the total water budget. I mean, it will just add to that, but still the water, I don't know how much it's going to change it, even if it doubled it, which, we have plenty of water already. And it places a little more water in the inner solar system, which is interesting. And maybe that does come about. And there's water in the moon too. And we don't have estimates of how much is deep in the moon. So maybe there's quite a bit. So that may mean there was more mixing in the formation of the solar system. So water was mixed throughout.
Roughly how much of the time will Europa Clipper be looking at Europa as opposed to other items in Jupiter system? Because if it is doing orbit on that thing.
Okay. We're only funded to look at Europa. We can fly by Ganymede, we can fly by Io, we can fly by Callisto, but we can't do any scientific measurements of them because of the limitations of the budget. But so we all decided we have to look at these other objects to calibrate our data. So there will be lots of calibration data.
Greg on the line is asking, did Cassini ever resolve individual ring particles in Saturn's rings?
No. Not with any imaging system. The radar system inferred the particle sizes, but not imaging. Okay.
This is a question about the periodic table of the elements. We found out fairly recently that Earth's periodic table was filled in the last half by merging neutron stars. Do we, with all of our data, instruments, and measurements, can we assume we know what it would look like, a periodic table of the elements on Mars or on Titan? Is it possible to assemble something, and would it be similar to Earth's periodic table?
Yeah, it'd be pretty much the same. We, the solar system was, you see these planetary disks around other stars now, and there's changes in abundance from star to star. But in our system, and most of the dust, the heavier elements came from supernova and other exploding stars, so the lighter elements, and the heavier elements, supernova. So that's going to be pervasive throughout the galaxy. There might be local variations in abundances, but all the elements are going to be pretty much everywhere, and just local changes. So on Mars, we see many of the same minerals, the same compositions as we find on Earth. And we also have Martian meteorites. The D to H ratio, I can go back. Here's Martian rock, old Martian rocks and younger Martian rocks. So as Mars evolved and the hydrogen escaped from Mars because its gravity is so light, then younger Martian rocks that formed will have a different D to H ratio. But the D and the H's are still there. So all of the elements in the periodic table are going to be, you're going to find them throughout the solar system. And pretty much, well, there are low metallicity stars and high metallicity stars that planets around those will have different abundances. So the solar abundances of elements will change from star to star, but you'll get most of the same elements.
David asks, is the phase angle important to image the plumes?
You want a high phase angle in order to see backscattered light through the plumes. And we've also done, with Cassini, we did 180 degrees. So we did transmission of sunlight and stars through the plumes. And the UV instrument was particularly good at that, detecting water molecules. At higher, the VIMS would see the 3 micron OH stretch, but we didn't from ice, but we didn't see that in the plume. They're just not dense enough. The signal wasn't high enough. But at slightly higher phase angle, we could see the diffracted light, and that showed that the diffracted light was scattered from crystalline water ice. That's another, you may read amorphous ice throughout the solar system. There's no amorphous ice throughout the solar system, anywhere in the solar system, except Europa, where the ice is being irradiated. When water condenses below 135 Kelvin and liquid nitrogen is 77 Kelvin, so the moons of Saturn are right around 120 to 130 Kelvin at the equator. Saturn's moons were about 95 Kelvin at the equator and colder at the poles, and then further out it gets colder. So it's expected that if that water condensed, it should be amorphous. It's not. It's all crystalline. All the spectra I showed were crystalline. I could show an amorphous spectrum and you'd say, yeah, it doesn't fit. And wherever we've looked, even out at Pluto, coldest there is, it's still crystalline ice. The only possible amorphous ice has been observed on Europa. And if you read anywhere else that it's amorphous ice, they're not interpreting the right data. Anything else?
Thank you, Dr.